Hey, what's up, guys? So today I want to talk about the expander graph and the famous result called expander mixing lemma. Okay, so to be honest, that uh, previously I didn't have background in the expander graph, but I find that the expander graph is somehow interesting in the graph theory and computer science. So I read some literature, and this is my first video about expander graph. And my YouTube channel consider mathematics, physics, coding, and whatever you like. Okay. Okay, so let me just create. So I will define expander graph and prove the expander mixing lemma. Okay, so let me just quickly say. So our starting point where we have a graph and a VE, and I think I will assume that G is a simple graph. So simple graph means that every edge is a bidirection, and also there's no loop. And let's consider the V to be n, and the E is bounded by n minus 1 divided by 2, right? Because it's simple. And I call it deregular. So deregular means that every vertices. So this is just some background, very simple graph theory. Every vertices has a D neighborhood. Okay, and let me also so from here that we get our famous adjacent matrices. So adjacent matrix. So let me just quickly remind you. So adjacent matrix is n by n matrices, and it's Aij. Let's say we label our vertices. Let's say from 1 to up to n. Okay. Sorry. Let's say v1, v2 up to vn, and the Aij will be 1 if vi, vj is in E. So basically, if there's an edge, otherwise it's 0. Okay, since it's symmetric, so Ag is a symmetric matrices. Symmetric matrix. Okay, so your simple linear algebra tell you that Ag is diagonal. And all the eigenvalues are real. Okay, so we can label lambda 1, lambda 2, lambda 3, up to lambda n. Okay, so a simple fact that I think it's very simple that you can simply prove this is that the largest eigenvalue must be D. Okay, so proof is very simple. You just and the reason is and eigenvectors will be 1, 1, 1, n1. Okay, the reason is that you can just check out yourself. AGV will be dV, because AG contains for each line it contains the D of it, right? It's deregular. Okay, so simple exercise. And the second fact is that all the lambda I will be minus D to D. Okay, so this tell you that this lambda 1 is actually do not have much information, right? Because you can take out different deregular and such that lambda 1 can be arbitrary, right? So lambda 1 always D, so lambda 2, lambda 3. So you at least need lambda 2 to give you the definition, to give you some information. Okay, so so usually we will define this lambda to be the spectral gap. So we call it spectral gap. Spectral gap defined to be the maximum of the absolute value. So basically, absolute value of lambda I, and the I is not 1, right? Because the first one is always D. Okay, so this is called spectral gap. Okay, so okay, so now let's talk about let's describe the so-called okay, so let's talk about the definition of expander graph. Okay. Actually, I think the expander graph and expander lemma they can take different can use a different approach. But let's quickly define expander graph. Okay, so expander graph is what? Is that right? Uh how should I say this? Okay. So how should I define how should I say this? Okay, so first I can define this h of g. It's called Higger number. Oh, sorry, not Higger. Higger constant. It's not Higger. So h of g is something that you define to be minimum of 0s less equal to n divided by 2 partial s. Okay. So this means that you take subset of the group. Not group. You take a subset of the graph, and then you take out the boundary. So boundaries is neighborhood. Okay. So and then you divide by s, and then you want to find this h of g. Okay. So usually the expander graph means that. Okay. So let me just write down something. Let me see how should I say this carefully. Okay. Okay. So this tell you that okay. So this tell you that somehow like so usually expander will have some parameter epsilon. So idea is that you want this h of if you choose all s, right? So this is a minimum s. So which tell you that so if h of g is less than s, then we will call this graph is expander g is an expander graph. And with the so usually parameter will say this epsilon if h of g is less than epsilon. Okay, so so your idea is that if epsilon is small. Oh, by the way, usually in the expander graph will require d to be regular. So you will need to require the graph is regular graph. So epsilon is small means that this g, right? So we can view this graph is just somehow like highly connected. Okay, but d but these should be small. Okay, so some quick notation we'll write we'll call G is ND lambda family. Okay, so when I say G is ND lambda family, means that the G is a graph with vertex n and the d regular and the spectral gap lambda. Okay. Okay, so now let's talk about the expander graph. Sorry, the expander mixing lemma. Okay, so this is our final results. Okay, so the idea is let's say VE and G is the lambda graph. Lambda is a spectral gap, D is a D regular, and it's a number of vertices. And for any S and T, let's say S and T is subsets in V, okay, then we can define EST. So EST is that every vertex is from S to T. Oh, sorry, every edge. So you consider X and Y, which is X product T. And such that the X, Y belongs to the edge. And then you count the, so EST is a number, which is a number of this. And okay, so this is a theorem. So theorem is that for every S and T we have EST minus D divided by N S and T. So the S and T means S and T absolute value means that the number of vertices is bounded by lambda and square root of S and T. Okay, so this is very interesting theorem that so this tells you that the expectation value of somebody give you ND lambda graph and you whoever you choose S, whoever you choose T, that the expander the expectation value or the average value of this edge between them should be bounded. Okay, and sorry, their expectation value is d divided by n s times t, and it's bounded, and the arrow is controlled by this lambda. Okay. Okay, so this is the first version, and there's a tighter bound, the tighter version that one can show this, and I will also prove this. SNT is bounded by lambda st 1 minus s divided by n 1 minus t divided by n. Okay, so proof is very simple. The ideal proof is that you start from, you just change this expression in terms of the adjacency matrices and use like a Cauchy-Schwarz. Since you know the maximum of the second one, right? So you can use this property to bound the adjacency matrix, the quadratic form of adjacency matrices. Okay, so let's go to a proof. Okay, so proof look like this. Okay, so how should I do this? Okay, so let's quickly define this one of S, right? So so one of S is a vector, which is if Vi belongs to S, it's 1. If Vi do not belong to S, it's 0. Okay, it's a vector. And let's notice. So notice what? So notice that this EST. Okay, so this EST is what? EST is that you just compute a 1S vector with the adjacent matrices and the 1T. Okay, so this is the first observation. Okay, once you observe this, then probably you get the answer. Okay, okay, and notice that what is SNT? Okay, so SNT is SNT can be written as a length of this 1S, right? And the length of this 1T. But you can also write this as 1S J 1T. Okay, what's J? So J is a matrix if you 1 1 1 1 1 1 1 1 1. Okay, so this is the simple observation. Okay, you have these two. Okay, so you have these two, then you can write these matrices EST divided by EST minus DN and SNT in terms of 1S T A G minus D divided by N J 1T. Okay, and you take the magnitude. Okay, so using your simple linear algebra, so this guy is what? It's bounded by the lambda of the. So this guy is bounded by what? This is the Cauchy-Schwarz, right? So let me just quickly remind you. So you can prove that your AX is divided by this, and so let's say this is Y. Y and X divided by the length of this is less or equal to the maximum, right? The maximum eigenvalues. Okay, or basically this is just Cauchy-Schwarz. So let me just quickly do this. So let me just quickly prove. So let's say you get YTAX and this, right? This is less or equal to, this is Cauchy-Schwarz YTAX. Okay, this is less or equal to YT, the norm of A and the norm of X. Okay. So or basically this can be proved. This can be bounded by the largest magnitude of eigenvalue. I should say the max of the absolute value. Okay, so it's max of the absolute value and the YT and X. Okay, so this is what you got. It's exactly the same as this. Okay, so once we have this 1ST AGD minus JT, then we got the answer, right? Because this guy, if you can call M to be AG minus D divided by NJ. Okay, and your goal is to write this one as M 1T, right? It's bounded by the norm of 1S and the norm of the 1M 1T. Okay, and this guy, you can prove this, right? This guy is bounded by lambda, right? The reason is that I already minus this, right? So the largest eigenvalue already disappeared. Okay, so this guy is bounded by lambda and T and Okay, and sorry, the length of t is the square root of t, right? And the length of s is square root of s. Okay, so you just use a Cauchy-Schwarz as I mentioned. So we prove the results, right? Because this is e of st minus d divided by n snt. Okay, so you just simply, actually I don't need to say this, right? But you just simply apply the Cauchy-Schwarz on this and this one, and the 1s of the norm is basically, sorry, I'm stupid. This is square. Okay, but sorry, I'm stupid. So this is square. This is 1st j1t. Okay, so if you take this, if you write this as this, then you write use the Cauchy-Schwarz, then you get your Cauchy-Schwarz inequality, then you get your answer. Okay, so let's go to the tighter version. Okay, in order to do the tighter version, that one that you just notice this, if you do 1s ag1t, this is s divided by n ag. Okay, so let me just let's say 1. 1 is a vector that every element is 1 ag t divided by n 1 plus 1s minus s divided by n t, one vector, and ag 1 t minus t divided by n 1 1t. Okay, so the reason is that you just do the expansion. So simple enough. So basically you can just do the expansion and prove this one. And this is the first one that we just mentioned, right? This is just n squared and s and t, and then you get 1 1 1 1, right? So you get 1 t ag1. So this guy will be n. Simple enough. You try to prove by yourself. And plus the remaining term, right? So the remaining term is a 1s minus s divided by n, and 1 t, y is here, and ag 1 t minus t divided by n 1. Okay. So this will give you s t n. Sorry. This is not because of d connectivity, right? So this is d. Okay, so d n squared. So it's d times n. Okay. Yeah. Okay. So d times n, right? Because for each line you get d, right? And then there are n of them. So you get dst divided by n plus something, plus this guy. Okay. Okay. So now you can see what this guy minus, so 1s tag1t is actually previously I just say this is est, right? So this guy minus this guy dstn. So this guy minus this guy is actually equals to this guy. Okay. So okay. So our final goal is to we just need to bound this guy, right? So this guy is very simple. So this guy is bounded by lambda times the square roots of 2 of the square roots of the length, right? So length of this 1s minus s divided by n1. Okay, and times this 1 of t minus t n1. Okay, so what is the length of this? It should be very simple. So 1s minus s n1. Let's take square. Right, you get a square, so it's 1s squared. 1s squared plus 1s dot with 1s divided by s divided by n plus s squared n squared and 1 squared. Okay, so 1s squared just the length of s, right? And then this is just s, right? Because inner product will give you s, the vertices, divided by n, and s squared plus n squared, this gives you n. Okay, so you can easily show this is s. Sorry, I forgot 2 here. Okay, so you get s minus s squared divided by n, right? So this guy is just s1 minus s divided by n. Okay, so you take a square root. Okay, so you prove this, right? So you take this guy, take the square root, you get s, square root of s1 minus s divided by n. Okay, so your final results will be there. So you get lambda s t 1 minus s divided by n and the 1 minus t divided by n. Okay, so which prove our the tighter bound of the expander graph lemma. Sorry, the expander mixing lemma. Okay, so proof is just very simple that you write the as this and then you just take the roots of take the coefficients. And then this lemma is very interesting. I mean, it makes me remind me about some number theory. Okay, so see you guys next videos.